ESGF is an international consortium and a globally distributed peer-to-peer network of data servers that use a common set of protocols and interfaces to distribute climate model output and related input and observational data. The open science data in ESGF are used by scientists all over the world to investigate the consequences of climate change and Earth system feedbacks. ESGF is developing a next-generation architecture, new data discovery interfaces, server-side computing capabilities, and analysis platforms for the next set of models from the Coupled Model Intercomparison Project, or CMIP. As an integrated research infrastructure, or IRI Pathfinder project, ESGF is pioneering the use of novel computing technologies for managing, analyzing, and visualizing data on storage and compute platforms across the DOE high-performance computing environments. ESGF holdings are open, large, and growing. Each new CMIP simulation phase produces more data than the last, and modeling centers participating in the upcoming CMIP 7 activity are expected to generate as much as 100 petabytes of new model output. All of these data are fair, findable, accessible, interoperable, and reusable. ESGF offers data discovery tools, including a programmatic search and retrieval tool called intake-esgf. The following provides an introduction to intake-esgf, a Python package providing a programmatic interface to the ESGF holdings. Intake-esgf data catalogs initialize empty and are populated using the catalog search function and providing facets or keywords with search criteria. In this example, we are searching for monthly mean output from the Canadian model that was run from 1850 to 2015. We would like the gross primary productivity, surface air temperature, and precipitation variables. This function queries a configurable set of indices and returns merged results in the form of a pandas data frame. Once the catalog contains the desired datasets, they may be loaded into memory with the toDatasetDict_catalog function. Internally, we are communicating again with the index nodes to consolidate access methods and locations for all the files that are part of each dataset. We use the following logic to determine how we will transfer or load your datasets. First, if a file already exists locally, we will simply load it. This may be because the file is already in the cache from a previous use of intake-esgf. It may also be because the user is working on a resource with direct access to the file. Second, if the user has indicated a preference to stream data and such access methods are available, we will harvest and provide these paths. Third, if the user has a destination Globus endpoint to which they prefer to download the data, they may provide the UUID to initiate a Globus transfer. As a last resort, we will download the remaining files using a threaded HTTPS transfer. The toDatasetDict function returns a dictionary of datasets whose keys are formed from the different facet values of the datasets returned. In this case, it uses the table ID and the variable ID. Note that intake-esgf also automatically includes cell measures, which in this case is area cell A. As a demonstration, we present a simple Python code to plot the temporal mean of each variable using matplotlib. From left to right, we plot the temperature, precipitation, and gross primary productivity. The programmatic nature of the interface is important because it allows the users to have a conversation with the index and learn what data may be appropriate to their science questions. It also hides the complexity about how the data is stored or made available to the user and automates many painful tasks. The interface also makes user scripts portable across systems, particularly important as server-side and data-proximate computing options become available. Large volumes of ESGF data pose a data migration challenge before computations can be performed. We are enabling scientific analysis on ESGF data by leveraging DOE computing platforms co-located with the data storage infrastructure. ESGF is enabling two data-proximate computing technologies. The first is Open Geospatial Consortium's web processing service, and the second is Globus Compute. The first technology is enabled by Rookie, the WPS client package developed and supported by ESGF. First, we import what we will need for this demonstration. This includes the Rookie package, which requires that we have an environment variable set prior to import. The rook URL variable points to the web processing service that we'll be using. We use intake-esgf to search for historical temperature data from 4 models. We use the catalog data frame to construct IDs that we can pass to the WPS client Rookie. Rookie provides the user with a set of operators that can be nested to perform a sequence of operations server-side. Here we write a function that uses an input rookie ID to load the temperature data, subset in time from 1990 to 2000 and in space using a latitude and longitude bounding box, and then average annually in time. Once a workflow is defined, we ask Rookie to orchestrate it on server side and return the reduced datasets. We use this function to operate on each of our Rookie IDs, loading the return datasets into a dictionary whose keys are the model names. As our workflow is executed on the server, we will observe messages indicating that the reduced result files have been transferred to our local system. As a demonstration of functionality, we loop over each dataset and plot the mean annual temperature of 1995 from each model using Matplotlib. Rookie is a great solution if your task focuses on a small spatiotemporal region and has low to moderate computational workload. This minimizes data transfer loads by reducing the data before sending it to the user. We used intake-esgf to help form the IDs that Rookie needs to remotely load data. A more flexible option supporting moderate to large computational workload is to use Globus Compute. For this demonstration, we will consider computing the El Niño Southern Oscillation Index. This is an important climate index built by combining some statistical measures of model output around the equator. Globus Compute can handle this custom workflow. It provides a mechanism to supply credentials, configure and balance our workload and execution environment, and retrieve the results of the computation. So, given a target workload, how do we start using Globus Compute? First, we write a function that uses intake-esgf to load data and then perform the desired operations. This function will need to be registered with Globus. Once registered, you can share your function with a user group of your choosing via globus.org. Now we will demonstrate this with the INSO example. Then we write, register, and test our function. Make sure that all libraries are imported in your function and also installed. The output of the function also needs to be serializable. In our example, we will compute the INSO index for two models, CESM2 and MIROC6. Our function takes a source ID as input, uses intake-esgf to locate and load data, and then compute the INSO index in an Xarray dataset. We first test it locally by passing a source ID, CSM2, and then inspecting the return dataset. Once the function is working, we need to initialize our compute endpoint. This requires that Globus Compute endpoint is installed, after which we run configure to provide an endpoint name and start to return an ID. We will use this ID, and so we store it now. Next, we set up an executor, which uses this ID and requires that ports are configured. We are now ready to compute. We launch our INSO function using Globus Compute on our endpoint. We do this by submitting two tasks to the endpoint, in each case supplying the source ID. In order to pull down results, we have to call each task's result function, storing each in a local variable. Once we have these datasets, now we can visualize locally. We have written a plotting function that we can call on both result datasets to study the INSO metric through the years. Then we use the Globus client to register this function. Providing the group ID allows all group members to discover and launch the function. This will return a function ID to which we will refer. We can run this function as before, providing a compute endpoint as well as the function ID we just created. Running this function returns the same result as before. Globus Compute is a great solution if a user needs custom computation near the data. As with Rookie, it also minimizes data transfer by returning only the results. In this case, intake-esgf was used to locate the data that already exists on the remote system, avoiding unnecessary downloads. Thank you for your interest and attention. Please use these links to learn more about ESGF, intake-esgf, Globus Compute, and the integrated research infrastructure efforts at ORNL.